All right, welcome everyone. We're about to take a really deep dive into the coronavirus family, specifically from a Dutch perspective. Now, just so you know, all the information we'll cover was compiled using Gemini Deep Search, and if you want to dig into the primary sources yourself, you can find a complete list in the Notebook LM document linked below.
So here's our game plan. We're going to follow a classic bench-to-bedside to community structure. We'll start with the virus itself, then get into the clinical side of things, and finally wrap up with public health. Let's jump in.
All right, Section 1, the dual identity of coronaviruses. You know, it's incredible how we went from thinking of these as just causing the common cold to seeing them as a genuine global threat. Let's unpack that.
You know, for the longest time, coronaviruses were, well, kind of boring. They were just responsible for about 15 to maybe 29% of common colds. Predictable stuff. But then everything changed. 3 major zoonotic events in this century. SARS-CoV-1 in 2003, then the incredibly lethal MERS-CoV in 2012, and of course SARS-CoV-2 in 2019, they just completely rewrote the book on this viral family.
Okay, on to Section 2. Let's get into the nitty-gritty inside the viral machinery. We're talking taxonomy, structure, and replication. What really makes these viruses tick.
So, at a high level, coronaviruses are enveloped, positive-sense RNA viruses. Taxonomically, they belong to the family Coronaviridae. But here's the key thing for us. All the human pathogens we deal with are in just 2 genera, the alpha coronaviruses and the beta coronaviruses. And trust me, this isn't just academic. This distinction is absolutely crucial because it dictates which receptors they use and, you guessed it, how much trouble they can cause.
And this table just lays it all out so clearly. Look at the sheer diversity here. You've got different receptors they latch onto, APN, sialic acid, ACE2, DPP4, it's all over the map. This variability is exactly what determines which cells they infect, and most importantly, it's the reason they have this terrifying ability to jump from animal reservoirs straight into humans. It's all right here in the receptor usage.
So why the name coronavirus? Well, it literally comes from its look under an electron microscope. It has this crown-like appearance, a corona, thanks to those big spike proteins sticking out. And let's be clear, these spikes aren't just for decoration. They are the master keys the virus uses to break into our cells. Everything starts with that spike protein. Okay, this is one of the coolest and scariest things about coronaviruses. You see, most RNA viruses are really messy when they copy themselves. They make a ton of mistakes, which means they can't have a big genome. But coronaviruses, they have a secret weapon, this proofreading exoribonuclease. It's like a spell checker for their genetic code. This allows them to have the largest RNA genome out there. And that extra genetic real estate is used to code for all sorts of nasty accessory proteins that are specifically designed to shut down our immune defenses. All right, Section 3, Diagnostics. Let's talk about how we actually find the virus. This is our bread and butter as medical microbiologists, moving from old-school cell culture to the molecular precision we have today.
This is so important for anyone doing lab work. The cell line you choose isn't just a detail, it can totally change your results. Just look at the difference between VERO-E6 and CALU3. One has the TMPSS2 cofactor, the other doesn't. That single difference dictates whether the virus enters through the endosome or fuses at the plasma membrane. So if you're screening an antiviral that targets one of those pathways, your results could be completely misleading depending on your cell line. It's a huge variable to control for.
And then we have the gold standard, right? RT-qPCR. It's fast, it's sensitive, it's what we all rely on for diagnosing an active infection. We go from RNA extraction to reverse transcription, amplification, and then signal detection. But, and this is a big but, the number it spits out at the end is way more than just a yes or a no.
And this is where the magic happens. That CT value, the cycle threshold, isn't just a number for the lab report. A lower CT value means a higher viral load, and that has been shown to be a powerful prognostic indicator. It tells clinicians, right from the get-go, that this patient might be at a higher risk for severe disease. It transforms diagnostics into prognostics.
Okay, so with that diagnostic background, let's pivot to treatment. Section 4 is all about the Dutch approach, focusing specifically on the evidence-based guidelines from SWAB EUA and the NHG.
When it comes to outpatients in the Netherlands, the approach is extremely cautious. Antivirals like nirmatrelvir/ritonavir are not for just anyone with a positive test. They are strictly reserved for adults at a very high risk of getting seriously ill, and you've got to start it within 5 days. We're talking about a very small, very vulnerable patient population. For the average person, it's not even a consideration.
Now, this is fascinating. When we look at hospitalized patients, there's a major split between the Dutch guidelines and what a lot of the world does. The SWAB guideline here says, and I'm paraphrasing, don't routinely use Remdesivir. The rationale is rock solid. Massive trials like Solidarity found no significant impact on the most important outcome, 28-day mortality. But then you look at international guidelines, like from the CDC, and they do recommend it. Why the difference? They're weighing other things, like shortening recovery time, which gets people out of the hospital faster. It's a really interesting debate about what endpoints matter most.
So, if the Dutch approach is hesitant on direct antivirals for hospitalized patients, what is the strategy? It's all about controlling the host's response. It boils down to a few key pillars. First, dexamethasone to tamp down that inflammation for anyone needing oxygen. Second, IL-6 inhibitors if things are getting worse and you see signs of hyperinflammation. Third, absolutely standard thrombosis prophylaxis with low molecular weight heparin, because we know this disease can cause clots. And overarching all of it is just excellent supportive care. It's a strategy focused on managing the patient's body, not just fighting the virus itself.
Okay, moving on to Section 5, let's talk about the long game, managing the threat of resistance and the absolute fundamentals of prevention.
This is a really sobering thought. It turns out that some of the key mutations that can cause resistance to drugs like nirmatrelvir were already floating around in the SARS-CoV-2 population before we even started using the drug widely. This means the virus didn't have to invent resistance from scratch. The potential was already there. For us in the lab, this just hammers home how critical continuous genomic surveillance is. We have to be constantly on the lookout.
And in our hospitals and clinics, the infection control strategy is pretty clear-cut. It's all built on a foundation of standard precautions for every single patient, and that means hand hygiene is king. Then, on top of that, you layer on transmission-based precautions as needed. Drop-it precautions mean a surgical mask. Contact precautions mean gloves and a gown. And for any aerosol-generating procedures, that's when you escalate to the highest level of protection, FFP2 respirators and, ideally, a negative pressure room.
Outside of the hospital, in the community, the thinking in the Netherlands has really shifted to a more sustainable, long-term model. Instead of focusing just on one virus, the approach is now syndromic. It covers all respiratory infections, or luchtwege infections. It's practical advice that works for everything. Stay home when you're sick, wash your hands, make sure rooms are ventilated. It's about building healthy habits into our daily lives, which is just way more realistic for the long haul.
All right, our final section. Let's wrap up by talking about ongoing vigilance and the massive role that we as medical microbiologists have to play moving forward.
So this is really the big question, isn't it? We know there's a huge animal reservoir for these viruses. We know they evolve. So how do we get ready for the next one? For our field, the path forward is pretty clear. We need to enhance our genomic surveillance to catch threats early. We need to keep pushing our diagnostic tools to be more than just a yes-no answer, but to provide real prognostic information. And we have to keep funding and doing the fundamental research that's going to lead to the next generation of vaccines and treatments. The job is definitely not done.
And that's a wrap. Thank you so much for watching. We genuinely love to hear from you, especially since many of you are experts in this field. Your feedback helps us make these explainers better, so please drop your questions, your insights, your critiques in the comments below. And don't forget to subscribe for more deep dives into virology and infectious diseases. Thanks again.